Today, I would like to discuss and share with you some of the work that we've recently done, even though this work was initiated 10, 12 years ago, but it has come to fruition only in the past 1 year or so. So I'm going to talk about some of the experiments that we do with single photons inside our laboratory. These experiments are meant to be a convenient training tool in quantum mechanics, quantum information theory, and quantum computing for our students and students outside LUMS, of course, as well as a sandbox for research in quantum optics and quantum information processing. So the working units of these quantum information processors, these are very simple quantum computers. They are photons, more precisely single photons. So we build a set of experiments around single photons, and this work wouldn't have been possible without this group of people. These are students from the UT Lahore, and I would really like to mention Hamza Wasim and Faizan Elahi, who were a part of this project. They completed this work under their final year project program. Faizan now is a master's student and he continues to work with us in some extensions of the experiments that I'm going to explain. Hamza, the other principal inventor or co-worker of in this project, is now pursuing a PhD at the Oxford University. And with the help of these students, we were also able to set up a repository or a suite of optics experiments that we now do offer to our advanced undergraduate and graduate students in the physics department. And we call this the Ibn Sahal corner for optics. Even though this picture shows only 4 or 5 people, there are other people who worked in the initial phases of this project. I would really like to mention Ramesh and Walid Khalid and Abdullah Khalid, who are our students who have now gone to greener pastures in the North America. So I just received this very nice image from our artist, for which was made for a different purpose. But these experiments deal with quantum light, and in fact, light, we are all familiar with light, but quantum light is something that is highly unfamiliar to us. One might argue that the light coming out from a laser is quantum light. That's not necessarily the case. Light coming out from a laser, though it is monochromatic, in most cases it could be collimated, it could be intense, and it could also be spatio-temporally coherent, but still it's not quantum light. It's the best kind of classical light, clean, well-conditioned classical light that you can make. In the parlance of quantum mechanics, it's a coherent quantum state. But if you really would like to go to the level of single photons and see quantum fields in action, or you would like to see light in the full glory of single particles, which we call single photons, then it's not sufficient to attenuate light from a laser or chop light out from a laser and have a sparser beam and a less dense beam in which photons are issued, or the beam is attenuated. You need to get to the really quantum level, and quantum light of this kind has a certain statistical signature, and this is what we explore in these experiments. And there are quantitative metrics that one could determine, especially what is called the second order correlation function, that helps us declare that the light that we're dealing with is quantum light. So the experiments that we deal with in the laboratory, they are directly probing quantum light. with a twist, and I'll explain that twist in a minute. All right, so let's so this is the basic kind of overview of what our single photon laboratory looks like. So this is a grand picture. So we have a laser, a very clean laser, very spectral, of high spectral purity. This laser falls onto a pair of crystals. These are nonlinear crystals, precisely beta barium borate crystals, and we have two of them, and they are glued to one another with their optic axis orthogonal to one another. And what happens when light at about 405 nanometer, which is shown onto this pair of crystals, most of the light, almost 100% of the light, goes straight through. It's transmitted. It just isn't affected by the crystal. But in a extremely rare event, some of the light emerges in the form of two beams, and this is a highly nonlinear process. And those two beams comprise of photons, of course, and the property of these photons in the two beams is that they are correlated with one another. And this correlation is not classical correlation. This is quantum correlation. And in the language of quantum mechanics, we say that these photons are entangled to one another. So one photon comes in, and in a nonlinear process, which is extremely rare, two photons come out. And of course, momentum and energy have to be conserved. So the wavelength of the emerging photons is double of the wavelength of the pump beam, the incoming beam. The frequency and the energies are approximately halved, and these photons are entangled. And the property, the degree of freedom that we are concerned with is the polarization of the photons. So light of a certain polarization comes into the pump beam, and two photons emerge. Their polarizations are parallel to one another, but orthogonal to the polarization of the pump photon. So this is a process which generates entangled pairs, and entanglement is a hallmark of quantum mechanics, as you all know. So these photons are entangled in their polarization, and we can write a quantum state for this photon pair. And they're not only entangled in polarization, they're also entangled in time, highly correlated in time. They are coming out at the same instance. And then we have two detectors, in fact, three detectors in a typical experiment. We can have four, we can have two, but the two beams are then negotiated or quantitatively measured with the help of these detectors. And these are special kinds of detectors. They respond to single photons. Since it's a highly rare process, if a billion photons come in per unit time into the crystal, maybe a few thousand would come out in the same amount of time in these two beams, which are called the idler and the signal beams. And these single photons now have to be detected, and we use special detectors called avalanche photodetectors. And when a photon comes onto the silicon surface of these detectors, they issue a pulse, an electronic pulse. So there are pulses coming out of detectors A and B, and these pulses are now counted with the help of a hardware, a piece of hardware which is called an FPGA, which stands for Field Programmable Gate Array. You can not only count the pulses, you can also find out whether the pulses are coincident in time, whether they're coming at the same point in time. So you can count singles, pulses from individual detectors, but you can also count the rate of coincidences. And then in each of these beams, you can put in some optical system, some optical experiment, and these are the kinds of experiments that we've built, which help us look at the properties of these photons. So in this case, we have a beam splitter, and the beam splitter has a transmitted beam and a reflected beam. So we have to insert an additional detector. Now we have three detectors, A, B, and B prime, and we can count A's or B's or B primes, or we can count the coincidences between A and B prime, and so on. And all of this information, and these are very fast pulses, by the way, of the order of tens of nanoseconds. So you really need fast electronics for this. And the FPGA, since it has a high clock rate, is able to implement this electronics. Of course, there are some front-end signal conditioning that needs to be done as well. But in any case, all the counts, they are then transferred to the computer and they can be analyzed. So this is like a statistical experiments like most other quantum optical or quantum mechanical experiments. And this is the holy grail. This is, in fact, uh, the whole idea of what our laboratory looks like. And this is a more realistic rendering. Another example of one of our experiments, laser comes in, it is steered into the pair of crystals. These crystals then produce two beams, in fact three beams. One is the unimpeded beam, which is just blocked and we don't care about it too much, and the signal and the idler beams that come at precise angles because the crystal has been cut in a specific way. And now you have two stations of experiments. You can call one of them Alice, you can call one of them Bob, and you can do different kinds of quantum operations on these photons, more precisely the polarization degree of freedom. You can implement quantum algorithms, you can do quantum teleportation if you wish to do so. You could look at the interference of photons and so on. So you get two distinct spatially separated experimental stations. One we can call Alice, the other we can call Bob. And why is this quantum light? This is quantum light in the following sense. One way of producing single photons is doing it by brute force. Suppose you have a single atom, just one atom in a cavity. You excite the atom by a laser pulse or by an electric field. The atom gets excited, the electron is at a higher level and it jumps down, it issues a single photon. So this is a very difficult experiment to build, and probably Dr. Taul-Haq might attempt doing this. But these are really sophisticated experiments in atomic atom optics. So, and these are difficult to do. And if you want photons on demand and you want a large number of them, it becomes even more difficult. First, how do you isolate an atom? Second, how do you make it behave like a sober sober child who is not derailed by the vagaries of the environment? And then how do you get a photon coming out of it in a particular direction so you can detect it? That's difficult. What we have here is heralded single photons. Now, heralded single photons means that if you look at one arm, say I'm looking at the signal beam, one arm that is going into the polarizing beam sphere. If you just look at the photons coming out on this, in this arm, in the signal beam, and you don't care what is happening in the other beam, then you don't get quantum light. You get classical, coherent light. But if you condition your experiments, that is only concentrate on the photons that have been generated when their cousins have been generated. That is, you look at photons in the signal beam that are coincident with the Adler beam. Or in other words, the Adler beam signals or indicates that there is a photon available in the signal beam. Then whatever you do with the signal beam, that will be quantum light, that will be single photons. You are doing an experiment in a conditioned manner. And this is how we can indirectly achieve single photons in the laboratory. And in fact, this process of down conversion, as it is called, a pump photon coming in, producing two photons which are entangled to one another, has made quantum mechanical experiments accessible in universities and even in colleges. And that's what we've tried to achieve. We think that quantum mechanics is not something that is locked up in a textbook and Griffiths is the beginning and end of quantum mechanics. It actually unfolds in reality. So this is the real image of one of our experiments, and this is not a rendering, this is a real photograph Here you can see a laser. It is steered by mirrors onto a crystal. There is a line which brings in dry nitrogen, and it just gently flows over the crystal because it is hygroscopic. It gets moisture, which deteriorates its quality. Then you have two beams, white beams, which are shown colored so that you can see where these beams are going. And then you can have different kinds of experiments in Alice and Bob. You can do 2-qubit experiments, single qubit experiments, and so on. In the path, you have different optical elements, quarter wave plates, half wave plates, polarizing beam splitters, and then these are collimating lenses that couple the light from free space into these orange optical fibers, and these optical fibers go here. Here they are going into a black box which is covered to make it opaque, and inside this black box are our detectors. And you don't want to expose these detectors to ambient light because that will burn off the detectors. These wave plates can be controlled by motors. Everything is controlled with the help of a computer program that we write. All the data is routed into computer through an FPGA. So it's a multidisciplinary kind of experiment which involves optics, electronics, and of course some serious quantum physics. This is a bigger view. This is our computer. There are some power supplies that power up the different components. A close-up of the laser, a close-up of the crystal, and these are our free space to fiber optical couplers. These are coupler adapters, and all of this goes into this 4-channel detector. From the channel detector, there is a signal conditioning unit which shapes the pulses. The pulses might not look really nice, so they have to be shaped a little bit and converted to the right voltages so that the FPGA can accept these voltages. And then all of this goes into a Labview program, which has a nice interface. This is the block diagram of the Labview program. And you can also conceptually decipher what's going on in an experiment with the help of logic gates. So I'm not seeing the chat box, so please, anyone is free to speak up or ask me questions in the middle as well. All right, so I've talked about spontaneous parametric down conversion. So a photon comes in and 2 photons are produced. So this pump beam is 4 or 5 nanometers. The signal and the idler beams are 8-10 nanometers. And I've already talked about heralded single photons. Gating of one beam at detector A projects the other beam into a single photon state. That's what is meant by heralded single photon schemes. You look at experimental outcomes on channel B only when there is a coincident photon on A. And since these photons are always produced in time entangled and polarization entangled states, you will be pretty confident that you're dealing with a quantum state here, a quantum field. That electron is bringing in a quantum field, and you can use quantum field theory or quantum optics as it is called to analyze the outcomes of your experiments. So this is, I've already described these pulses then go into a coincidence counting unit which is hardwired into the FPGA. This is what, by the way, a single photon pulse looks like if you see it on an oscilloscope. By the way, our human eye, the human retina, is also sensitive to not to single photons but say a couple of dozen of photons. There are some marine animals that can respond to single photons. Single photon is really important if you would like to do astrophotography, in which signals are coming up from very far and you have very dim objects to image. So this pulse has to be conditioned. It has to be made into a nice TTL or a CMOS pulse, squarish shape, so that it can go into an FPGA and is ultimately detected and counted. Now, there are different kinds of light, and I've mentioned quantum light. If you look at the statistics of quantum light, the red graph, which shows the probability of detecting n photons, is squeezed is tighter with respect to the Poissonian or the super Poissonian light. So there are different ways of looking at the quantumness of light, at the particle, the grainy nature of light. One is looking at the histogram of the times of arrivals of photons. So I won't go into these details because this requires a separate foray into quantum optics, but let's get to our experiments. So this is the archetypal experiment. This is the experiment which has to be performed in the first stage and which will help us ascertain that we are indeed dealing with quantum light. So light comes in, it is down converted, and then you have one photon in the arm A and one photon in the arm B. Let's call this Alice or Bob or Signal and Idler. One photon in Bob's possession. This photon is now a single photon because it has been conditioned by the emergence of a pulse here. So we're working in a quantum subspace. This single photon can now be impinged onto a polarizing beam splitter. It has the photon has some polarization. You can change the state of polarization with this half-wave plate. The polarizing beam splitter has a property that it routes horizontally polarized photons in, say, the transmitted arm, and it routes the vertically polarized photons in the reflected arm. So if you have a single photon coming in, the photon can either go to B or B prime. You will never have a positive correlation between B and B prime detections. You will have a negative or an anti-correlation between B and B prime. This means that a single photon cannot be split. It has to take one route. So this is, now you're looking at the particulate nature of light. You're probing or negotiating single photons. Of course, this will only happen if you are performing a decision on these photons when a coincident click at A is present, which will ensure that you're dealing with single photons. So this is the parameter that is derived from basic quantum optics, which is called the second order correlation function. It's a correlation between intensities at two different times. So in the numerator, you have P, A, B, B prime, which is a threefold coincidence between A, B, and B prime. So you count the number of threefold coincidences between A, B, and B prime in a certain interval of time. That gives you a count rate. You divide this by the twofold coincidences between A and B, and the twofold coincidences between A and B prime, and this ratio will then give you the second order correlation function. And quantum light, in the absence of experimental uncertainties, has a second order correlation function of 0, right? Exactly 0. Pure classical light has a second order correlation function of 1, coherent state, and something beyond 1 is called chaotic light, or the light that comes out from an incandescent bulb, for example. So we are interested in determining this second order correlation function. So you count the A's, count the B's, count the B primes, look at the twofold and threefold coincidences, make a table or have a computer program do all of this for you. And looking at these statistical outcomes, you look at this quantity, and you'll find out that this quantity is less than 1, which is a signature that this is indeed quantum light. It's not exactly 0 because, of course, in an experiment you can't get 0, but there are accidental coincidences, and we can determine those accidental coincidences. We can predict them, and our predictions match the experimental outcomes. So we do have quantum light. This signature, this G2 naught, is a fingerprint of whether you were dealing with quantum light or single photons. So this is a modern version of the classic Hanbury-Brown twist experiment. Now, once you have a single photon, it can be described by a ket, all right? And in this ket, there are unknowns. There is a complex or a real number A and a real number B and a real number phi. And there are 3 unknown parameters, A, B, and phi, that you would like to determine. Since the state is normalized, there are 3 unknown real parameters, and we can now determine these parameters and measure these parameters through a sequence of experiments in which you position certain quarter wave plates and half wave plates into Bob's beam, uh, orient them in different directions, and do a measurement and infer from your measurements the value of these coefficients. So you can gradually build up an estimate of what the quantum state is going to look like. Of course, you can't do it in a single experiment with a single photon, because your experiments, your measurements are destructive. They're projective measurements. Once the photon goes onto the detector, it loses its existence. It is annihilated. So you need to do a sequence of experiments on identically prepared photons, which hopefully are coming out from the BB crystal. You can input different kinds of states that you generate using this combination of a half wave plate and quarter wave plate, and then you can measure. And you can do all kinds of interesting experiments. Sometimes we do an optical version of an experiment called polarimetry, antenna polarimetry, and we get these very nice hypopedal patterns on quantum light, and we also do it with classical light, and this is a very useful way of determining quantum states. By the way, we should remember that it's never single shot. Now I would like to come to one of our major experiments, and that is of quantum interference and erasure. So I would just like to highlight what is a Mach-Zehnder interferometer. Any questions at this stage? Sorry, I'm not looking at the chat box, but any
Sabieh,
questions?
the questions are being asked and fielded by Dr. Ata, Adam, and others. So that's continuing. The participants can directly talk to you at the end of the webinar.
So I can continue batting.
You just continue. Yeah, you just continue.
All right. So light comes into a Mach-Zehnder interferometer, and the Mach-Zehnder interferometer has a beam splitter at its entrance port, which produces 2 paths for an incoming photon, and then these paths are recombined, and you can see some kind of pattern on a screen. You can either see a blob which does not have any structure to it, or you could see an interference pattern. So you can polarize the initial photon that comes in, and if these 2 polarizers in the individual arms of the Mach-Zehnder interferometer are parallel to one another, you will hopefully see interference fringes. This is how a Mach-Zehnder interferometer works. This is how gravitational waves were detected, for example. However, if the polarizer P1 and P2 are mutually crossed, then these orthogonally polarized photons cannot interfere, and you will see the absence of an interference pattern. In other words, if you get a photon here, by looking at its polarization, you can tell whether that photon has come from this lower arm or the bottom arm. In other words, these polarizers are tagging the path of the photon. A photon, of course, cannot be split. So the photon has to take either of the paths. But if you have some knowledge about the path of the photon, you will not observe interference. So holding or harboring which path information washes away interference. Which path information means that you have knowledge of the localization of the photon. You know that it's a particle, so you won't see interference, which is generally hailed as a wave phenomenon. So you can either see the wave property or the particle property, and this is why Mach-Zehnder interferometers have a special place in experiments that deal with the foundations of quantum mechanics. So you can in fact do a series of experiments, and these are experiments from our experimental setup with classical light, with laser light, in which you can rotate polarizer 2 through a sequence of angles starting from 0 degree all the way up to 90 degrees, and the visibility of these fringes keeps on dampening with time. Now this is an interference experiment, and you can do a clever trick. You could place a polarizer after the interferometer and still have crossed polarizers which in one sense would have removed the interference pattern because you would have obtained which path information. But quite interestingly and counterintuitively, placing a polarizer after the interferometer, after the photons have traversed the interferometer, can recover the interference pattern or erase the which path information. So this looks like a very counterintuitive idea, but it makes perfect sense in terms of quantum fields and quantum mechanics. This is called the erasure experiment. And this is, we found this to be one of the more difficult experiments to perform with quantum light. So this is the background of quantum erasure. And now we can do it with our experimental setup. In our experimental setup, you have exactly the same idea. And now our interferometer is not a Mach-Zehnder interferometer, rather it is a pair of beam displacing prisms, which act like polarizing beam splitters. They separate out the horizontal and the vertical polarized photons. Then you have a half wave plate, which is positioned at 22.5 degrees with respect to the lab frame. Light at 45 degrees is coming in. What this half wave plate does, it swaps the it makes horizontally polarized photons go vertical, vertically polarized photons go horizontal, and then a subsequent beam displacing prism recombines the beam to look at the potentiality of interference. And interference, of course, has to be with respect to some parameter. In the previous example, this parameter was the difference in path lengths between these arms. These are automatically available in these experiments because the beam is divergent. But in this case, we are dealing with collimated beams and single photons, so we have to have some control over a parameter which changes effectively the path length. And that is controlled by rotating one of the beam displacing prisms through an angle, phi. So, and finally, you have a polarizer at the end. If this polarizer is at 0 degrees or 90 degrees, then you will have the which path information and interference will not be observed, but having this at 45 degrees will wash away the which path information and quantum erasure can be seen. So these are results of our experiments which beautifully match the theoretical predictions, in which either you can change the input polarization of the photon that comes in here, and these are the outcomes of the two detectors A and B, of course conditioned by the presence of a photon in the idler beam, or you could change the orientation of the incoming polarization with the help of another half-wave plate. So we have clear signatures of quantum erasure and quantum interference in our experiment as well. And as I mentioned, if you were to change this angle, the angle of this polarizer, you can control the visibility of these interference fringes. By the way, this is interference of a single photon because you're only dealing with single photons. So you change the polarization of this ultimate polarizer just before the detector, you can predict what visibility of fringes you will observe, and you can measure them. And these are what the interference fringes look like, plotted against the phase difference between the horizontal and vertical beams. All right, so this is quantum mechanics in full glory. And as Feynman said, if you can understand the interference experiment, you can understand most of quantum mechanics. And this is how we not only understand quantum mechanics, we can also observe it with our little eyes. Now, the second kind of experiments that we perform, they deal with non-locality and the violation of local realism. Now, local realism is a slightly philosophical concept, but it's very easy to understand with the help of some toy experiments or Gedanken experiments. Locality means that, in very naive terms, something that Alice does not affect what outcomes Bob measures. So two stations that are spatially located, their outcomes are going to be independent of one another. And realism means that you want to measure something, the object has a certain intrinsic property, and you just measure it. And even if you don't measure it, the property doesn't change. So if local realism is correct, and it was argued that most of nature works based on the principle of local realism, uh, in 1964, John Bell proposed certain quantitative measures that can test local realism, and those inequalities come under the umbrella name of Bell's inequalities. And there are different kinds of Bell's inequalities. So you can put you can put local realism to experimental tests. And if we have quantum light or entangled light, most of these inequalities, they are violated. And we've performed a series of experiments that look at different inequalities and find out quantitative measures, and our quantitative outcomes, they violate the Bell's inequalities, which means that nature ultimately does not respect local realism. And if we're dealing with entangled states, uh, local realism has to be made a part of the dustbin. So there are different kinds of tests that we do. One of the most famous tests, which is and also one of the most difficult to perform, is called the CHSH test of local realism. And there's a lengthy but comprehensible derivation of this inequality. The outcome is that one can define an S, a parameter S, which is a sum of the expectation values of joint probabilities or joint events A, B prime, A prime, B prime, A prime, B prime, which are really orientations of these half wave plates. So one orientation of this half wave plate and one orientation of this half wave plate will give a certain value of A, B, A prime and B prime. Then you change these orientations and you ultimately you need to find out these expectation values, which are averages, and then you form a sum and you get this S. And this is how we define each one of these expectation values. E alpha beta is the joint probability of detecting a horizontal polarized photon on A and a horizontal polarized photon on B, and so on. And if this overall quantity is less than a threshold of 2, it means that local realism is correct. Otherwise, the idea of local realism is jeopardized. So we prepare an input state, which is an entangled state called a Bell state, and we orient our angles of the half wave plates to certain positions, and we finally do a statistical analysis of the outcomes that we get, the twofold coincidences, form the appropriate sum, find out our S, and observe that this is 2.331 with an uncertainty of 0.004, which is far, far, far away, many standard deviations away from the threshold of 2. So we violate local realism by many orders of magnitude. I think 2 orders of magnitude here. We can do other kinds of tests which are simpler to understand but could be equally difficult to perform. One of these is the Hardy's test. It's a simpler test to understand and comprehend on a piece of paper, but slightly difficult to to experimentally verify, because you need to create a certain input state which has precise coefficients 0.8 square root and 0.2 square root. And if you get a positive value of h, which is defined in this fashion, local realism will be violated, and you'll be urged to believe that quantum mechanics is non-local and non-real. So we perform the experiment, and once again we violate the inequality by about 50 standard deviations. The third test which is the simplest to understand and the simplest to perform. And one of the earlier Bell's tests is called the Friedman's test of local realism. Once again, this delta, this parameter delta, if it is less than 0 or negative, we'll have to respect local realism. But we perform the experiment with a certain optical arrangement, and we violate the Friedman's inequality as well. Now, the last part of my talk deals with tomography. And there are two kinds of tomography that we are able to do. Excuse me. One is state tomography, and the other is process tomography. In state tomography, you are measuring a quantum state. In the prior experiments, we assumed that the quantum states we have, the single photons, they are pure quantum states, but that is not necessarily the case. States can be mixed. They can be highly mixed. An entangled state can be intermixed with the maximally mixed state, for example, to create a Werner state. So these states are really, in real terms, they cannot be described by wave functions. Rather, they are described by this object, which is like an operator. It's called the density operator. And this density operator is given as a convex sum of direct products of Pauli operators. This is one way of representing a density operator. So finding a state means finding out these parameters, which are called the S's. And the ultimate goal of state tomography or quantum state tomography is to determine this, in the case of 2 qubits, a 4x4 density operator. So how do we do that? We have to perform a sequence of well-known quantum optical transformations. Or we have an input state which is unknown, and we apply a series of unitary operators on that state. And we then recreate the experiment with a different initial state and perform the same sequence of unitary operations. So it's like doing tomography. If you would like to do tomography of the human body, for example, you shine a radiation on a certain angle, you get a certain projection. Then you shine the same kind of radiation but at a different orientation. So you slice your body at different orientations, sagittal and dorsal and ventral, and then you recreate from all the data that you've gathered all of those projections, and they are tweened together, they are coupled up together in an intelligent fashion to recreate the entire body. And this is exactly what we do in quantum state tomography. You input different kinds of input states and have precise unitary operators act on all those states. Sorry, in quantum state tomography, you input your initial unknown state and put a sequence of quantum unitary operators, one after the other, one after the other, one after the other. So you're projecting your input quantum state onto different planes. And from what you observe on those planes, you can recreate the entire initial state. This is quantum state tomography. So, for example, we created this, in one experiment, we created this Bell state. And when we did tomography on this, ideally in this Bell state, you should have just the corners of this density matrix populated, right? So 0.5 here, 0.5 on this corner, 0.5 on this corner, 0.5 on this corner. But we weren't able to create a pure state, and we did quantum state tomography, and this is what the density matrix looks like. And then once you know the density matrix or the quantum state, you can find its fidelity, you can find the degree of entanglement, you can find concurrence, etc., and do all kinds of pretty stuff. You can find Fisher information, what kind of information is contained in the state, and so on. And there's an algorithm that is based on the maximum likelihood technique, which reconstructs your parameters from the available data. It's an overdetermined system, so you have to do it really carefully. There are certain constraints on the density matrix as well. So we create different kinds of states. These are the predicted density matrices, and these are the experimental outcomes from our single qubit experiments. Could also do 2 qubit experiments, You can create different input states. These are separable states. This is an example of a Bell state. It's easier to create separable states. The fidelity is high. These are the predicted density operators, whereas these are the measured density operators. And then you could also do process tomography. Suppose you want to know, you know what the state is, but you don't know what the process is, what the unitary operator is, or even a non-unitary operator. So this is called process tomography. In process tomography, you input known states, measure the outputs, and from those outputs, you would like to determine what the process is. What process has the input state undergone? So in this kind of experiment, you vary the initial states. You have the same process, but you put in one state after the other, one state after the other, and from the outcomes, you infer what the process could have been. And the process could be a unitary operator, it could be a super operator, a non-unitary operator, which can be defined in pretty ways. So we did this non-unitary process tomography, and our process was a magneto-optic experiment. So light comes in into the signal or the Adler beam. It is polarization manipulated, and then we have a crystal, a garnet crystal, which is placed in a cryostat, which takes the crystal to very low temperatures, about 5 or 6 kelvins. Everything is placed inside a magnetic field, and you do a magneto-optic transformation, which involves a rotation as well as the generation of ellipticity in this crystal. And then you do your quantum state tomography, and from the results you try to infer what is the process that is being affected by this magneto-optic element. And the process is defined by a process matrix chi. From this process matrix, you can construct the super operator, or what are called the cross operators. And if the process is close to being a unitary operator, which we found it indeed is, because these photons do not decohere easily, you can also map the process for different magnetic fields on the Bloch sphere, and you can infer certain interesting properties of the polarization ellipse of the single photon. All right, so this is all that I had to share with you about some of these experiments. Now I have an undergraduate student, Bilal Haider Shah, who is going to recreate some of these experiments as a part of his preparation for the final year project, which hopefully is going to be some more interesting and exciting extensions of this work. So that's all that I had to say today. I'll be happy to take questions.
Thank you very much, Sabieh. So we already have a couple of typed questions that haven't been answered yet. Rushan Bukhari is asking if whether you think that this seminar and its principal findings could be condensed and packaged for a younger audience, like A-level/FSC students. He's interested to know that, and I assume he wants you to then go ahead and deliver that talk as well.
I think yes, indeed. These the beauty of these experiments is that these experiments can talk to a very sophisticated audience, and they can talk to an audience who is at the younger level, at the FSC or the A level or even the O level. Some of these experiments can be packaged in the form of take-home kits as well. Technology has become cheaper, but you need someone to do that, and you need the time to do that. But of course, these ideas can be easily metamorphosed for a younger audience.
Okay, great. Asif wants to know your degree of confidence that you actually obtained single photons and not just continuous beam of light.
Well, the degree of confidence is about 50-60 confidence intervals. I mean, you look at this graph here, sorry. So this is 0.080, which, and if you, this is much smaller than 1. And if you look at the standard deviation, 0.005, you can subtract 1 minus 0.08 and divide by 0.005, you will find, I think, about 100 standard deviations, just 100 standard deviations away from the classical prediction. I don't know how more confident can you be. So it's really quantum light, and this value is still finite, it's non-zero, and this is perfectly explained by the accidental coincidences, and one can do a quantitative measurement, an estimate of what those accidental coincidences could be. What is the meaning of accidental coincidences? It means the following. One, these detectors have dark counts. So even if no light shines on them, they produce about 300 or 400 counts per second. You can get accidental coincidences because of these dark counts. It's also possible, especially if you have high flux rates, that you can have a coincidence between one pair and a subsequent pair, or a following pair, or a preceding pair. That will also give you a false positive, right? So all of these false coincidences can be determined because you know the probabilities, you know the rates, and you know the time intervals, your coincidence window, which by the way is very small, it's about 20 nanoseconds here. And you can precisely predict what those accidental coincidences are. And these values are within the accidental coincidence range. So we are, I would say, dead certain that this is quantum light. You look at the violations of local realism, they are far, far off from the inequalities by tens or in some cases 100 standard deviations.
Talha, can you unmute your mic? Can you see if you can possibly unmute your mic and just ask your question? Talha Sajad. Okay. I can't be sure. Let me see.
So he's asked about technological advancements.
Okay. Yeah. So yeah. Okay. So I think he doesn't have permission to ask, but I guess you've just seen the question. He's asked two questions. So the first question is about the meaning of violating the inequality during the entanglement tests, and the other question is about what kind of technological advancements can we expect from single photon experiments.
Right. So the meaning of the violation of inequalities means that if quantum mechanics is local and real, so if it satisfies local realism, you can devise an experiment with a certain quantitative outcome, which is expressed in the form of an inequality. If that inequality is satisfied, then nature has to respect local realism. Otherwise, if the inequality is violation, that is, then your states or nature have to be non-local and non-real, which means that if Alice makes a measurement, it will immediately determine what the measurement of Bob is going to be. But if Bob is going to do an experiment on his own, in his own universe, without resorting to sharing results with Alice, then Bob is going to get a seemingly random string of outputs. But when Alice and Bob perform this seemingly random sets of outputs, and when they merge together and compare the results, they find perfect correlation or anti-correlation between these results. This is what entanglement is. So Alice's outcome, in a sense, is determining what Bob is going to measure. So this is an example of non-locality, and this is after precluding or not allowing communication between Alice and Bob to take place. So they are so far away that they share their results even before the possibility of light traveling between the two stations allows them to secretly share any results. So this is violation of non-locality, and quantitatively it is expressed by the violation of these Bell's inequalities. The other question about technological advancements is that if you would like to build true quantum computers, and using photons is one way of doing that, and photons are really advantageous because even if you were to build quantum computers using ion traps or superconducting qubits, you have to share information from one computer to another, which is called a quantum network, and you can't shuttle ions or superconducting circuits which are at 1 millikelvin from one location to another. You need some workhorse that can become the messenger RNA, the messenger taking messages from one quantum computer to another and make a quantum network or a quantum internet. And those could, at the moment, to the best of our knowledge, could only be photons. So single photons are really important, and that's why they are technologically important. Most of quantum communication or secure communication is done with single photons. That's why this is really important.
Eamon, you should now be able to ask your question. Please go ahead. Unmute your mic and go ahead.
Can you hear me?
Yes.
Okay, my question is from process tomography. As it was clearly mentioned that the temperature is up to 5 or 6 Kelvin. So how to achieve such low pressure temperatures? And what is the benefit of it?
So you can achieve these low temperatures by making a refrigerator. And in the refrigerator, instead of having in older refrigerators you had freon gas or some chlorofluorocarbon. In modern, it's been banned since 1979. You have these new refrigerants or coolants that flow in refrigerators. But if you want to really go in these low temperatures, you don't use a coolant of this kind or a perfluorated carbon, rather use helium gas. So if you use helium gas and put it in a refrigerator, you can get really low temperatures. So this is how we get these temperatures. And what is the benefit of it? You would like to look at how the process changes with temperature, how the process changes with magnetic field. Crystals change their properties with temperature. Solid state physicists would always like to vary the temperature. So we determined the temperature dependent quantum processes, and we observed that the rotation operator changes and it can be mapped on a Bloch sphere as the temperature varies. So this is just an academic pursuit of seeing how a particular quantum process can change with temperature.
We're now down to the last question by Rushan. Rushan, you should also have permission to speak, so go ahead.
Thank you very much. So my question is that, Dr. Sabieh, is there a reason to choose a particular wavelength of light that is shown towards the BBO crystal at the beginning of the experiment? And also, are the results of the experiment altered with different wavelengths? Thank you.
Yes, so the reason of choosing this wavelength is the following. There are a couple of reasons, perhaps. One is that our detectors have a high efficiency in a certain wavelength regime, and that wavelength regime is the near infrared regime. So you work your way backward, you can find out what the wavelength of the pump beam should be. So our detectors have a high efficiency above 650 nanometers, and we're dealing with 810 nanometers. And if you want to do type 1 spontaneous parametric down conversion, it requires an incident pump beam of 4 or 5 nanometers. And it's easy to get, and then you have to find out whether it's easy to get a laser at the required wavelength of the required spectral purity. So it's easier to get 4 or 5 nanometers. It's harder to get, say, 420 nanometers, or the next easiest wavelength is 488 nanometers. So you have to look at the technological availability, you have to look at the cost, you would look at the efficiency of the detectors as well. So this is, and we would like to do experiments mostly by experience. I do most of my experiments in the optical or near infrared regime. I don't go to the telecom wavelengths. Dr. Imran Chima, I think, who's in the audience, would like to do these experiments in the telecom wavelengths. But so all of these factors contribute to the choice of the wavelengths. You don't want to go into the UV because then your optics becomes really expensive as well.
Thank you very much, Sabieh, for a very interesting talk, and I'm glad that people chimed in with their questions. Just for the participants, as the semester begins, you should expect these seminars to happen on a fairly regular basis. The goal is to have one every 2 weeks, if not every week. And so we hope for your enthusiastic participation for all future seminars. Have a good day, everyone. Bye-bye.
Right. Okay. Thank you. Bye-bye.